the structure would like to follow its own way to transfer the load, the natural way, right? And it's like water. When you put the water somewhere, it will flow in the direction of the maximum slope and the least resistance. The same thing is that the loads, when you apply it will go through the stiffness. So stiffness is like the medium through which the load will flow. So the load, when you apply somewhere, it will try to follow the stiffness where it guides it. So it's not that there's a natural tendency of the load when you apply it to go in a certain direction, and that path is predetermined by the structure's stiffness and the load location. So that's how it will move by itself if you don't disturb it, if you don't interfere with it. That's the natural path of the load flow. And it's just like water, right? But sometimes we can reverse the water flow by pumping it back, against the gravity. We will force it to go another way, right? And not the way it is going, which means that we have to spend some energy, or we have to make some additional alteration in the structure, which will not be the least cost. It will have additional, effort to force the water against the gravity. Same is the case with loads. If you want the loads not to go the way they want to go, you have to spend some extra effort to do that. But sometimes it will become necessary to do that. So as structural engineers, our first job is to find out where the load wants to go, which is the path it wants to take naturally. Then, is that path acceptable to us or not? And if it is not acceptable, how can we change the path and make it go another way, right? So so this is kind of, in this particular example, this is the natural flow. But typically, we assume that point from here, from floor slab to beam, beam to girder, girder to column, column to foundation. But actually, this load can go directly from the slab to the column also. And we will see later about that. Now, this one is a load from, once again, this is the slab. There's all the live loads on it. From that slab, it is transferred to the beam, from beam to the column. But this transfer, this is very important, is from the slab to the beam and to the column, right? But what if there's no beam? Then what will happen to the load? What if the beam is very small? What if the beam is very large? So based on the stiffness ratio of the beam and the slab, this path may not be as it is, because load, if there is no beam, the load can go directly to the column because there's no beam. So if you apply the load on the slab, from the slab, it will jump to the column directly. And just because you introduce the beam doesn't mean that the load has to go to the beam. Beam has to be strong enough to deserve that load, to attract that load. So only then it will go through that. So which means that the load is going to follow the stiffness path. And I will present that. I will discuss more detail about that later. So just remember that the gravity load path is not what it seems or not what we would like it to be. We have to find the real path first, and that is through analysis. So this is another gravity load path. You can see here from the roof to the slab and all of and then this one again, once again, we go from this one to this one, columns, and add up of the foundation all the way. So once again, the load path within the door, where there's a door, there's an opening, there's a load coming from the top, there is a window opening with there, the load will go around that, go back down there. So the transfer of the load vertically will try to go through the available structural elements based on their stiffness. And we have to determine that properly. But typically for tall buildings, that path is only part of the problem, because most of the tall building, like I mentioned to you, is not about the gravity load. The gravity load is important and it will be a contributor, but the major challenge is lateral loads. So let's talk about both of them. So I will talk about this load transfer a little bit more for the gravity in another talk focused on this subject. But coming back to the global tall building system now. So if you look at the gravity, then it can, so from here, we are saying that the gravity load will transfer to the column to down, and to the foundation. In this case, this is an alternate system. There's a columns going all the way, so it's fine. Let's say there is a building which is primarily a cantilever. We have seen so many buildings in which cantilever slab is the main structure because of the form of the building. So in that case, load will go to the wall and wall to the down. So we have to create a mechanism to transfer the gravity load from the floor slab to the wall, and from wall down to the beam, down to the foundation, because there is no columns in this particular case. Then if there is no core wall, which is also possible, like the diagrade system, some other system, which there is no core wall, you only have the skin. So the load will go to the skin and skin to the down, right? So this is the primary, very rough way, 3 ways that you can bring the gravity load down. One is through the columns all the way down. One is through the core all the way down. One is through the external framing and all the way down. So this will work in tube. This will work in diagrade. This will work for core system. That will work for frame system. Yep. So this is roughly the way the load can transfer. And then lateral load. So this is interesting now. If the lateral load is wind, so wind will be applied first to the walls. From the wall, it will go to the column. From the column, it will go to the floors and all the way down and onto the foundation. During this process, it will deform the building and so on. But it will start with the walls, cladding or glass, from glass to the columns and floor, from that to the vertical system. So gravity load will flow like this, and lateral load will flow something like this. So the columns will get both the lateral load and the gravity loads, as I mentioned last time when we talked about this system. So sometimes the load path will be interrupted. Like I said, multi-use buildings, there is an entranceway. Nobody likes to have a column there. So columns are coming from the top, and suddenly columns will be stopped. So all the gravity load coming from the floor to the column down here, now it cannot go further. So you have to now transfer it in others. So that this is what I'm saying, that you disrupt the natural flow of the load by moving it to the alternate system. So this transfer girder and transfer slab will be needed here, which we will talk about that in another talk. So basically, all of the gravity load coming here suddenly moves to, and this creates several problems. The first, most important one is construction sequence. And once again, when we do construction sequence analysis, I will give you this example, the difference between not doing construction sequence and doing construction sequence. You will get totally different results. So if you have a part like this, construction sequence is very important. So alternate way to transfer, sometimes people just carry the load up rather than bringing down, because at here you do not get the space to put the girder. So you take the load and you put an arch or a truss at the roof and carry the load column backs, hang it from there rather than transfer it here. So it could be here, it could be intermediate. This is very common. You would provide these transfer slabs or transfer girders many places, because this is maybe the swimming pool area or there's a community area. Many buildings have these days. So they bring the columns, then they want an open space, then start again. So we have done several buildings of this kind where they melt every 15, 20 floors. There is a atrium, there's a high floor with trees growing there and pools and whatever not. Okay. And then start again. So there are multiple blocks stacked like this. So you have multiple load transfer systems. And this is an interesting system, which is often, but it's like every few floors, it will be. So this is called a wear and deal truss. It's not very common, but it still is used sometimes. Okay. So bridge or girder transfer systems. So this is a good example in a real building that all the columns are coming and suddenly there's this huge beam there, which will now transfer it to these columns. And then, so this one you can see from here, and then you need the transfer girder, which will be concrete or steel. A lot of things need to be done for this transfer system, which is very common in tall buildings. A lot of the time it is used. And sometimes we investigate intentionally what will happen if one of the column is broken or one of the column is destroyed for any reason, right? Blast or accident, or car is hitting it or anything. So what happens if one of the column is blown out? what will happen to the building? What will happen to the load transfer? So we designed the building to go like this. We did not design a transfer girder here, but suddenly one column is gone. So what will happen to the building? Then we have to make sure that we have an alternate in system to carry if one or two columns are accidentally or whatever reason are broken or failed, right? And many buildings these days require this redundancy to be investigated, especially for important buildings that and we did last time a thesis that, which column is important? How many columns can you take out from a building before it collapses, right? And you find surprisingly that a lot of columns can be taken out and the building won't fall because there is a redistribution mechanism in the building. Because of the stiffness, it carries the load back to distribute to other places. It will have a deflection, but not failure. Okay, so that is something that in fact, there was a building in India, and it's similar to this one. So they wanted to check whether one of these big columns, because there are only 8 columns left finally on the ground. What happens if one of those big 8 columns is broken? And we found that even with that, the building will still be possible to be standing. It's like it's like a table. Sometimes you can see with 3 legs, it's still standing, right? So that's the kind of thing that you need to sometimes do the evaluation. So that is for that alternate load path to see how it will move. This is also important for foundation settlement, that if one soil is weak under one footing, what will happen to the load? Okay? And so that's also can be investigated, that what if this foundation fails, one of the foundation fails, what happens to the building? So these are all scenarios that you might need to consider depending upon what the client wants. So this is if there's a blast here broken, then what will happen to the load? This transfer mechanism is built to do that. So alternate load path. So many ways are doing. You could go up, take this way, go this way. So many systems have been developed to check or create alternate load paths into the structure. Sometimes without adding anything special, just checking what are the other paths available if something goes wrong. Okay, so that's just to talk about the load transfer mechanism. So it's like I said, load has a natural way to transfer, but we can always find an alternate way to force it to go another way. Okay, or it has to go another way because of some failure. So on the very basic level for the lateral loads, we have bearing wall system. That means the lateral load and gravity loads is taken by wall, solid wall, nothing else, solid wall. And this is quite common in tall buildings up to 20 stories. People just make walls. So those walls serve as partition walls and also structural walls. So there is no column, there's no beam, just walls. Okay? And this is becoming quite common, especially with precast systems. This is building frame. Building frame is a very special category of frames introduced not too long ago, where the lateral load is all carried by the walls and gravity load is carried by the columns. So the frame or the column or the beam do not participate in the lateral load. It's completely separated. So lateral load, walls, gravity loads, columns and walls. So the beams and columns do not participate in this one. That has to be designed specially, building frame system. This is very good for steel buildings where you can put very simple joints. So you can save a lot of money on joint design and just put only one wall to carry the lateral load. And this is the moment frame, which all the lateral load is carried by the beam and column and the joints. And this is a big mixed dual system, walls plus frame. So these are the most common. This is most common for tall buildings, medium range. This is 15 to 20. This can be done for 30, 40-story building also. And that is also possible. So all these are possible systems in concept. These are conceptual, basic systems. And then you can do many things from these. You can build up more complex systems from there. So gravity and this one, building frame and bearing wall. So bearing wall and gravity, this is a combination of the two, the lateral load systems. And this is the frame, moment resisting frame and dual system. We will talk about them now today. So there is a big difference between the two. Gravity load and lateral load. As I told you in the beginning, one slide, challenges are gravity load and lateral load. So the difference is the direction of the load is vertical, direction of the load is horizontal. Obviously, it's quite obvious. This is directly imposed on structures. This is reversible in nature and is cyclic, and it is sometimes because of the movement, not because of the load, like earthquake, right? It's mass generated. So the nature of the lateral load is very different. The gravity load is from the density and applied load. Do not produce fatigue. They can produce fatigue. These are deterministic, not deterministic, not easy to determine. What does it mean, deterministic? Actually, not deterministic, really. For example, we are saying the live load here for this room is 2 kilonewton per square meter or 2.5 kilonewton per person. But how many people are sitting there? How many people can fit here? So it's just an average. It's just a statistical number determined from how much one person weighs, how many people can fit here, and so on. But if you really think about it, for live load to be 2.5 square meter, this is like 12 by 8, so almost 100, right, square meter, roughly. So you need a lot of people, hundreds of people here to reach that load level. So normally the live load is overestimated, except for storage and other facilities. But in any case, it can be estimated. But wind and earthquake, not easy to estimate, because we don't know the wind velocity, and we don't know the direction, and so many things. Earthquake, we have no, we have to make many assumptions where the earthquake is happening, what is the intensity of the earthquake, what is the ground, soil condition, and so on. So not easy to determine. Deformation is small, deformation can be large. And this is, mostly flexural member, this is vertical members. So there's a major difference. You can read more about that. I need to go a little bit faster today. So for the gravity loads, we have these typical systems. You have slab supported on walls, like I said, wall system, wall and slab system. So no columns, directly slab supported on walls. This is beams, secondary beam and column system. This is rib and beam and column system. And this is also rib and this is like a waffle slab system. So you have several systems for the floor slab to be done. This is flat plate and flat slab. This is the most common system these days for tall buildings, flat slab and even flat plate, post-tension. Okay. And normally, like I said, mentioned to you before also, building codes do not allow this to happen. So you have to create a building frame where all lateral loads are taken by shear walls or alternate systems. And gravity load does not participate in the lateral load at all. So columns and slab do not do anything. It's the building frame, the shear wall, or the framing system that does that. And we will talk about that. So this is just a figure. So that's a flat plate. This is a flat slab. The difference between the two is that the flat slab has a drop panel over the column to reduce punching shear. So we put that to reduce punching shear and also to reduce slab thickness and reduce the weight. So this is more economical, much more economical than flat plate, unless it is post-tension. But the problem is the casting is difficult, construction is more complicated, form work is needed, so people do not like it. This is more systems, baffle slab systems with the drop panels, and this is a building with several systems, ribs here, beams here, baffles here. So just showing you how different floor systems are possible for tall buildings. Or any building, for example. So basically, you have a flat slab, you have a flat plate, you have beams, you have beam slab, you have ribs, you have joists. So 5, 6, 7 names for the same thing, depending on the size of the thing. So beam becomes a joist if it is narrow. If the beams are closely spaced, it becomes a waffle, and so on, right? But the concept is the same. We are trying to minimize the weight of the gravity load as much as possible. So we need to choose the system which has the least weight and least height. Waffle system basically reduces the weight, because waffle system is basically you have a big slab with the stiffness is very high, reinforcement is very slow, but you take out all the concrete that you don't need, because you are taking out, because most of the concrete in a slab is not used. It's on neutral axis. You just have a tension bars which take the tension. We have a compression at the top, which is small depth of the the concrete that is needed. Rest of the concrete is useless, practically useless. So the idea is to take out as much of that concrete as possible. So it can be done by taking the waffle slab or doing the rib slab. Rib slab is one-way waffles. So you just keep the same depth and take out all the concrete that you don't need. So because stiffness comes from the depth. Reinforcement design is based on depth. Weight comes from the thickness. So you're trying to balance the two. The problem is the cost of the form work. Making them is very hard. You have to have special form work, special, it's very costly. So some people, don't like it because it's difficult to make. So all these systems have been optimized over the years. And so I can just tell you roughly, if it is not a tall building, because tall building, the depth is also an issue, and the construction speed is an issue. Waffle slab is the best if you want to have long spans, minimum columns, because you can go up to 12 meters. This is about 12 meters. That long without any columns can be very far. So waffle slab has the ability, because you can make it deep with least weight. So it gives you the least weight, it gives you the long spans, so you can reduce the number of columns, you can reduce a lot and give big spaces. But the problem is making it is hard. So some companies have special forms, plastic forms, that they use multiple times. So if they can use the same form like 20, 30 projects, then it's okay. But if you only do one project, it's not viable. So flat slab, this is the easiest to make. Just put one form very fast. Because normally in a tall building, they want to achieve one floor per week speed, which means it has to be extremely fast. You have to put up all the form, you have to cast the concrete, you have to remove it within 1 week. Some projects, 5 days, 4 days per floor. Very, very fast construction. So if you do that, then everything has to be flat. You don't want any problem. You just take out the forms, move to the next floor, and do it very fast. Let's come to now how to develop the structural systems. The serious, based on all this discussion, let's get into a little bit more detail on what systems are there and how they are structurally, what is their response, how do they develop, okay? So this is an interesting book, which actually you have seen a lot of the images from this book. I borrowed from this, it's a German, I think, and Understanding Vertical Structural System. It's a nice book. It's an architectural kind of a thing. Mostly architects use it for understanding the structures, but I think engineers can also use it. And I have borrowed many slides from this book. So this is also from the same book. So it's best telling you in very simple concept, layman term, how does a system, tall building system work, right? And I think being civil engineers, you already know, but I just want to make sure that you understand that when you have the lateral load, you get the lever arm at upward, downward reactions here, and then vertical reactions created, and you get a drift. So columns get axial forces up and down because of the total moment. And then you also get the total tilting of the building. So building deforms in several ways. Please, this is very important for you to remember that a tall building will deform not in one way. So it can show you one way is axial shortening of the system. Second way is tilting of the whole building. Another way is the shear deformation between them. And so you have shear deformation, which is like this one. You have flexural deformation, like a cantilever, like this one. And you have the overturning at the foundation, tilting at the foundation as a rigid body, another one. And then you have the axial shortening. So 5, 6 different deformations happen in the building, which contribute to the total deflection of the building. And as an engineer, we should find each one of them separately, because each one of them has different meaning in the check, right? So drift is this kind, shear deformation between each floor. We are very concerned about drift. Overall deflection, we are concerned because for the overturning and so on. So we have to check each one of them. So these are the primary ways the building can deform due to lateral loads. And they are all independent phenomena combined together to get the total deflection of the building. And this is the lateral deformation. So it's a little bit more clear. So you have this way, which is basically that the joints are not working. Each column is independent. When you connect them together, it becomes like a frame. So you have bending moments and deformation relating that. This one, if you brace it, it becomes like this. So it's very clear diagram of what happens if the only columns are working and floor beams are not working, like a flat slab. Flat slab will be like this. If you have a beam and column of the similar size, it will be like this. Beams will deform, columns will also deform. This way you can see columns are not deforming. Columns are just bending like a cantilever. Each column is bending independently because the slab is not stiff enough to force the column to rotate. It's only connected in a small place. If you have a beam, the beam will force the column to rotate, and each floor will have local deformation of the column. Stiffness will increase. And then if you put a bracing, that floor will become almost rigid. It will not deform. So then the total deformation will be reduced. From this one is very large, here and here. It's a relative thing. But this is on concept. This says a lot. So if you have only vertical element independent, like columns and flat slab, no stiffness, nothing. It will just have nothing, no lateral resistance. If you have a frame, it will have much better. If you have braced frame, even better. But each one of them has its limit. So this system can work maybe 2-3 floors. Beyond that, it won't work. This system can work maybe 15 to 20 floors. Then this system can go beyond that, and so on. So we have different systems going in different heights. And this one you can see once again. So if you put the bracings in there, this one here. So if you keep them independent, these two separately, it will be like that. If you connect them together, they become like that. So you can brace them in different ways. This is a very good diagram to understand the concept of coupling that I mentioned to you last time. So if this is one, let's say this is a building, and you think of this as one frame, this as another frame, and you don't couple them together, they will bend like this. And when you couple them, this will bend like this will bend like this. This will act like a frame. This will act like a wall. And when you combine them together, it will act like this one. And then if you want to brace it locally, you can brace it in that way to also do the things. Gradually increasing the bracing as you go down, because the deflection will be, accumulative. Okay. So please look at this diagram, because after this one, we will go into more details of how this system works. So primarily, look at this here. When you connect them together, the columns the floor is no longer straight, because this can be considered as a wall, shear wall. This will force the columns to go up and down. Axial forces will be generated on the edges of the wall when you couple it together. Okay. Second thing you should observe is, if it's a frame, it will deform like this. Maximum deformation will be, it will become almost straight as it goes up, right? It will start to deform like this and then go up straight. That's a frame deformation. The wall or a brace deformation will go like this. It's vertical here and become more inclined at the top. This one almost vertical here and then vertical at the top and then goes down like this one. And this is the effect of the bracing. So depending upon where you put the bracing, you can change the response. So if you put the bracing everywhere, it becomes like this from the original one. If you put bracing, so these diagrams are extremely helpful in concept on how to put the bracing, how to connect the wall with the column, how to alter the deformation pattern by using different framing systems. So if you get, this book is free on the internet. If you can download that, you can learn a lot from there. So once again, this is frame shear wall interaction. I will show you more later. So it is the frame. It is a simple frame. It can deform a lot. And then this is a frame with more sizes of columns and beam. That is very small columns, big beams. This is big columns and big beams. And then this one is braced. This one is braced by concrete. This is a concrete wall. Very nicely showing 3-4 variations of how you can create a frame. Okay. And each one is used as a separate system. So this is more like a beam and small columns. This is a frame of large size. moment frame, true moment frame. This is a braced frame. This is a infill wall plus frame, and this is a shear wall plus frame. Okay, so you can see here several systems on the same side by side, all of them designed to improve the lateral performance from the original one. And sometimes we can tie it down. The building I showed you in Dubai, they actually followed this concept. This book was published a long time ago. At that time, nobody thought that somebody will actually make the building which is braced by cables. But that he did that. He built that building braced by cables, just like this. But actually, these cables can be brought. Look at the architectural simplicity of the idea. Watch this carefully. So he put the cables first like this. Then to save the space, he moved the cables to the inside using the same. So you get same effect, and then modify the building to be internal bracing like this, concrete. So instead of cables, you use concrete member, and then another way. So people have followed all these concepts in building design because architects look at these things in this way. They develop the systems gradually from simple one by altering, adding something and making it very natural. And then from there, form will come up. Okay. So this actually comes back to the big discussion of form follows the function or function follows the form. So in engineering, we think function should come first and form should follow. But architects say, no, form should come first, function should follow, right? And sometimes it's both. So it shows you that combination here. This is a very important document, minimum design loads and associated criteria for buildings and other structures, issued by ASC, American Society of Civil Engineers, latest 722, right? Document 7, year 22. So they tell you many things about how to do the detailed design of the building with all of the stuff. And it gives you the factors of R factor. But right now, what is interesting is not, we will talk about that later. But there are, for each system, like bearing wall system, they have several subtypes, many subtypes listed there. If you go back, you will see this bearing wall system. There are 21 types of bearing walls in the code, right? For each type, they have given some numbers. And those numbers are the deflection factor, the overstrength factor, the response modification factor, and also seismic, you use which zone it is, and no limit, and P, not permitted, and no limit, and limits. So basically, the design codes will tell you which system you can use in which kind of seismic zone up to what height, right? And what factors to use to design it. So everything is codified. You take that table and you read the numbers and then you put it in your design criteria and then go from there. But most engineers do not like it because most of these heights, this is 100 feet. 100 feet is nothing, 33 meters, right? 30 meters. We're talking about 300 meters. There is no mention of any building with that kind of height, 1,000 feet height in this one. So which means these codes do not work for tall buildings. And we should not try to use them for tall buildings because they're not meant for that. There are different codes and different rules and different things for that. Okay, so we must look for those different guidelines. But anyway, this is a good starting point in any case. So based on that code, we have bearing wall systems, fully braced systems, moment resisting frames, and dual system. Let's talk about them one by one. So this is the story, the limit of the stories with different systems developed by some, it's not absolute limit, just an idea. For example, flat slab and columns, less than 10 story. Flat slab and shear walls, 20. Actually, now flat slab and shear walls can go up to 50 stories with the use of outriggers and use of other systems. Okay. Then flat slab, shear wall, and column, coupled shear wall, rigid frame, widely spaced, and then all of that. Many systems are written here, right? So which means that you can keep developing the systems gradually until you can go to as high as possible. And we are going to do that now. Okay. So this is a nice document from this guy, Moon, strange name, Moon. 2018. And according to that, so these are internal systems. That means the things that you put inside the structure. Okay. And then he has 7 braced hinge frame, concrete rigid frame, steel, concrete plus shear wall, plus frame, plus staggered truss, plus this, plus, many things here until we have, this is the outrigger system that I talked to you about, and we're going to talk about that. And but buttressed core in this one. So this is systems which are inside the building, which is fine. But I told you last time that a lot of people are moving the systems outside the building to the skin of the building, not inside, because inside people don't like it, right? You waste the space. So they are moving it outside. So these are the external systems that are on the face of the building. So there you can see here concrete frame tube, steel frame tube, tube in tube, concrete base tube, and so on and so on and so on, until this is called the super frame conjugate towers, multiple towers connected to each other. And this one, according to him, you can go up to 240 stories, like 3 kilometers high or something like that, right? So which means that if we follow this idea, you can go very high. Super frame, this one, up to 160, braced mega tube. So external systems are the answer to super tall buildings, okay, which we are not doing, right? But ideas are simple, ideas are interesting. We should learn anyway. But internal systems are the one that we are interested in because they are going up to 100, even these are going up to 100 stories, right? So we will study both of them today. So let's look at these systems now one by one. So primary system discussion will be focused on internal systems and external systems. So I want to discuss with you today the concept behind them, why they work. What is the structural mechanism under these systems? So we understand why they work like that. Okay, so that's what we are going to do. Let's start with a simple one. The most common, simple, which everybody knows, moment frame. So moment frame looks like that. So you have columns, you have beams, and everything is based on the flexural and shear stiffness of the columns and beam and the joint. So the assumption is that the joints are rigid, and anything happening to beam can transfer to column. Anything happening to column is transferred to beam. So that is the definition. You can read about that. So basically, if you take one joint, any joint here for lateral load, you will see that there is a column, there are some beams and columns in different locations, and there's a joint in between that, and there's a joint here. So basically, the entire system relies on the rigidity of the joint. We are assuming that this, look at this one here, that the moment here in the column and beam are transferred to each other completely without loss through the joint. Now, here, it's probably a good time for you to also note that the gravity load, the moment is generated in the beam first because of the gravity load, and then transferred to the column through the joint. Clear? But for lateral load, it's the opposite. Lateral load, the building will deform first, which means it will produce the shear in the column first. That shear will generate bending moment in the column, and that column bending moment will transfer to the beam. So the way the forces are generated is opposite. And this is extremely important and useful for us to know when we go to the design, that gravity load comes from the vertical load causing bending moment in the beam, deformation in the beam, that causes the joint to rotate, which puts bending moment onto the column. Lateral load is the building is trying to deform by each floor, that causes shear in the column, which causes moment in the column, which causes moment in the beam, which causes shear in the beam. So that flow is completely opposite. Vertical load, shear causes moment in the beam, moment in the column, shear in the column. This one, shear, moment, shear. Completely opposite. So when you combine them together, actually we shouldn't be able to combine them together simply because they are very differently generated. And this is something that we will talk about when we talk about the design of this one, these things. So you can see here that bending moment is created, shear force is created, and axial force. All of that are created due to horizontal load. So we apply the load horizontally, but you get bending moments, you get shear, and you get axial forces in the frame. Okay? So even there's no gravity load, you will still get axial forces, but they will balance each other. That will be zero because there's no vertical. So equilibrium, total vertical forces in the columns will be equal to zero because there's no vertical load. So you can see one is red, one is yellow. When you add them together, one is positive, one is negative. When you add them together, it will be zero. And this total shear here, which is all yellow, will be equal to the horizontal load. So the equilibrium will be followed like that. This is called base shear, total shear at the foundation level, called base shear, very important number, and equal to the horizontal loads. Okay, and this is the bending moment generated in each column and each beam. So every component in the frame gets activated when you apply horizontal force. Gravity load, if you apply on one beam, it only remains on that beam. But for horizontal load, you apply one horizontal load to any floor, the whole frame will get activated because deformation is transferred everywhere. First time when I tried to do a building like this one, it was not that very high, 7, 8 stories without computers, without anything, and try to figure out how to do this, how to calculate all the bending moments in the frame. So we used to have what we call a cantilever method. So basically, you can see the observation from here that on center of every column, the moment is zero. And that's a very interesting observation. You can start with that idea that the center of the column, each column, the moment is zero. So you can apply a force at that location and calculate the bending moment from half the column height. And from there, everything can start. So this was called cantilever method of building. And that's what they used in all the tall buildings before computers. No matter how tall the building is, it's always using the same method, cantilever method. You cut the building at this level, you get the total force, and you calculate the shear first here. And from that force, you calculate the bending moment by using half the height of the floor, force multiplied by the half column height, you get the moment. And then from that moment, you calculate beam moment and shears and everything. That was how you did that. So let's look at now frame behavior. 3 examples that I ran. Please watch carefully. This one is using small column, small beam, so it's a flexible frame. This one is using large beam, small column, because the span is large. So we're putting a big beam there. And this one is using large column and flat slab. Right? So 3 different variations. And we want to study what happens to the bending moment distribution and displacement in these. So you can understand what is going to happen and what you should alter. Many people might think that making the column large will be the solution to resist the lateral loads. You will find that is not true. It's always the beam that you need to make stiff. If you have a problem with the horizontal lateral displacement of the building, you cannot solve it by making the column bigger. You only solve it by making the beams bigger. Okay, we will see now. So if you look at the displacement now, you can see easily that this displacement is that much, this displacement is less, and this displacement is large again, right? So we made the column very big, but the displacement didn't happen. We just made the beams big, displacement is half of the frame, right? So that's clearly, and that is because beams are long, so their stiffness has to be increased to provide enough joint stiffness. Columns are anyway short, so the small size will not matter. If you change, it won't matter. So that is lesson number 1, that if you want to control the lateral displacement of a building, always focus on horizontal members, not on vertical columns. And you can also see now the bending moment patterns here, this one, and this one. You might not see something, but please watch carefully. Here, each column has a bending moment, negative, positive, red and yellow, red and yellow, red and yellow, red and yellow, red and yellow. In this case, it's all red. which means the column did not get double curvature reversal. It's acting like a cantilever. All the moments are only in one direction. Each column is acting independently like a cantilever. That's why it did not help. It did not create the frame behavior. So here, beam moments are large, and then the column moments are smaller, and they are reversing every time. So they are benefiting from that. Okay. So these kind of observations are very important to do this. We can also put haunches in the beams. At the ends, we can make the size, increase the size, so you get benefit from there. So you can increase the stiffness. If you put this flat slab in the frame, then you end up with a big problem, because flat slab is very flexible. So it bends very easily, like you showed, like you've seen in this system here. This one, this is a flat slab. So it bends very easily. It cannot rotate the column. So it has no lateral stiffness. So it doesn't help in the lateral loads. So that's what happens. The slab just bends, and it just creates no significant stiffness, lateral stiffness for the structure. So if you want to use that, low-rise building, you can still use, where the lateral diff is not important, forces are small, up less than 10 floors, 5 or 6 or something like that. Sometimes you can use drop panels. It will help increase the stiffness of the joint, so it will help a little bit. And sometimes waffle slab is very good because the depth is quite large, and you use drop panels together with that. So waffle slabs can go up to higher floors. So this is what I write here. You can read that. Let's come to the next one. So moment frames, we are clear. Beams must be strong. Beams must be deep if you want to make the frame effective. But the problem is what? Architects won't let you do that. I told you that if you increase the beam height, you are cutting into the total height of the building, because that will multiply by 50 floors. So you will lose the height available. And then if you make the beam very deep, they have to put the ducts, they have to put the piping, they have to put the air conditioning. Everything will be disrupted. So nobody wants beams in a tall building, not anymore. So beams are not a good option for tall buildings anymore. Arched beams is okay. You beam like this, something like that. That you increase the size of the beam close to the joint and then reduce the height in the middle so people can still use it, but you increase at the joint haunch and it increases the stiffness. So this is another option some people can use, haunch beams. Okay, braced frame is, as you have seen, bracing is very useful, very helpful, because immediately locks the shear deformation of the entire frame. So you can add the bracing at various locations in some of the frames, and it will greatly enhance the lateral deflection. In fact, a lot. So it's almost like putting a wall there. So shear wall and frame and braced frame are almost the same in behavior. Both of them lock the deformation in one panel. It doesn't allow the panel to deform. So if this is a panel here, and if you apply horizontal load, this panel will deform like this. If you put a brace here, then it won't deform, because you're preventing this displacement by the axial force produced in the wall, in the brace. So that will not allow it to move. Same thing can happen if you lock it by a wall. Same thing, shear deformation will be locked. So either the wall or a brace work in the same way. They lock the panel and they prevent it from moving. And if one panel doesn't move, nothing moves. So that's the advantage of the brace frames. So you can have different kinds of bracings, mostly for steel. You can see over there shapes, all kinds of bracings are used. But bracing is quite helpful for wind and steel building. Concrete, very hard to make a brace. Not easy to make an inclined column, or jointing is so hard, the reinforcement is all messed up. So normally in concrete building, very difficult to use braces, unless it's a steel brace that you put inside the frame building, concrete frame building. You can also do bracing like this, K bracing, knee bracing, V bracing, inverted V bracing, but you can see mostly low-rise building, mostly steel, but they are very effective. And for tall buildings, we use the BRBs. I mentioned to you before, buckling restraint braces, because braces are not good. We will talk more about that. But basically, braces attract a lot of force. When you move it, it will get a lot of force. and then it adds a lot of stiffness, but it will buckle. It doesn't have a good ductility. So we don't want braces, ordinary braces in tall buildings, especially for earthquake. For wind is no problem. England, no issue. Philippines, no, right? So in that case, we use this new type of braces called buckling restraint braces, recently invented. Recently means maybe 10, 20 years ago. And then we use them in buildings like that. So you put the braces between the column, between the outer column and the core wall, and that acts like a brace and also outrigger and also damper. So it's many advantages. Okay? And we will discuss that when we come to this idea. So then we come to bearing walls, core walls, and coupled walls. Various types of walls that you can use to carry the structural system. So this is the various walls. So this is these are the independent walls. This is a core wall, I-shaped, core wall, C-shaped, and this is just the total tube, right? So basically you just put walls there in the building, a lot of walls, either independent or core or combination, or couple them together, link them together. So this is from a real building. This is a wall-only building. So you can see there is no column here, blue things. All of them are red, which are walls. So the whole building is just walls and slab, which is so nice for a residential building, small apartments. Every partition is a wall, concrete wall going all the way to foundation. So the concrete wall is also the structure, is also the partition. So you save a lot of money and time. And especially with precast, this is very good. And recently, we designed one building in Thailand, I think 35 stories high, all made from precast walls, precast slab. So wall, because it's not easy to make the wall on the site. So they make the wall in the factory, bring it, erect it, post-tension it, done. So it's very, very fast and very good system, very economical system for tall buildings, especially for residences. And then we have the core. As I told you, core is very important. So there's a core wall, core wall, core wall, and around that column. So core wall is which contains the elevators. Around the elevators, you use that portion to create your main primary core. We talked about this quite a bit. And you use that core basically to carry the lateral loads. So it's quite now possible to use a core with post-tension slab. Look at this one, what I'm talking about. There is no column, there is nothing there. Okay, so this is very interesting because it completely eliminates any beams from the floor, just outer columns and core, and all the lateral load carried by the core. Wall has nothing to do with it. So you don't need the framing action. So this is quite useful, and these are all from real buildings. So that is an example of the same thing from real building. We have just the flat slab and the core, nothing else. And this works fine because lateral load is carried by the wall, core wall, all of it, and the flat slab and column doing nothing for lateral loads. So this is the core location. You can have the core here, core there, cores like this. Obviously, this is the best one. We try to do that. This is not so good. This is also possible. This is also possible. This is not good. This is not good. We will talk about what's good, what's not good on core wall locations when we talk about the dynamics and the mode shapes and the dynamic response. Okay. So this is, once again, typical core wall locations. This can be like this and this. So you can distribute the walls in many locations. This is a good configuration, poor configuration, fair, and so on. So just, roughly looking at that. But actually, it's not always possible to do what we want. Architects will govern this. So sometimes we have to accept poor configurations. Sometimes we have to accept a configuration layout which is not the best and have to design for it because that's what the building demands. So it's not always possible to get what we want, but at least we should know what the problems are and how to fix it. So now we come to the second interesting part, coupled shear walls. Shear walls which are connected together. We talked about the coupling effect. Right? 1 + 1 not equal to 2, more than 2. So we come to that idea. How do we do that? So basically, we talked about the coupling effect, that we connect them together and we take a lot of benefit from that. Okay? So coupled shear walls, basically, this is what you do. So if it's an elevator, normally there's a door for the entry into the elevator, and then we put the beam at the top, and that's called coupling beam or link beam. Very, very important part of the structure for the tall building, especially. And then automatically, and sometimes we just take some walls and then door openings, window openings, and then use the portion above as coupling beams. So we create these coupled walls by simply putting holes in the wall for windows and openings, right? But basically it's one wall. Or you take two walls and you connect them together. Either way, you can think of this way or that way. So what happens now is that this coupling beams are subjected to when the wall will deform, the two walls will try to deform, then they will deform this beam also, and this beam doesn't want to deform, so it will try to push the walls back. So now this deformation in each wall is resisted by the shear deformation in the coupling beam. And that is the fight that we have to sort of resolve. Which one wins? Do we allow the walls to win in deforming, or do we put the coupling beam so strong that it pulls them back? Sometimes the coupling beam becomes so strong that they break because they attract too much shear, but they cannot carry it, right? So there is the biggest challenge is how to, as you can see from here, they're cracking now because because these walls are huge and the coupling beams are small. So when they try to pull them back, they break in the process. They're not strong enough to do that. So they break themselves by trying to connect the walls. So now the choice is that you make them big, but the problem is you can't make them too big because you will block the opening, right? So then what is the next choice? We talked about ductility, we talked about the capacity-based design, we talked about allowing it to yield. So basically we limit so the way to design, and we'll come to the detail, but just now you're talking, we limit their capacity to carry shear by limiting their moment capacity. We go the other way, backwards, because we don't want them to break in shear. So to prevent that, we can limit their moment capacity, and from there backwards limit their shear capacity, because the moment capacity will not increase beyond the certain limit, and because of the shear is created by moment, reverse, not here, the shear is coming from moment. Remember, I just explained to you a few minutes ago that in a lateral load, the beam, first of all, the moment is created and shear is created because of the moment. So if you limit the moment, you can limit the shear. So you can allow it to yield for a certain level so that it will not fail in shear. So it will become like a ductile beam with a certain capacity. So it will resist the movement until some point, then let it go, but will not break itself, right? It's a beautiful concept because it will try to stop the walls from moving as long as it can. And beyond that, it will say, okay, fine, you want to go, let it go, but I will not break. Then we'll absorb that movement by ductility. We talked so much about ductility, right? So we make these beams ductile, and we use the capacity-based design procedure to make sure that they will never break. Yeah, so the reinforcement at the top and the bottom is limited. We do not calculate the reinforcement from the moment coming from the design, but we calculate based on the maximum shear that can be produced. So we reverse calculate based on capacity design procedure, right? So we first of all calculate how much shear it can take and what will be the moment corresponding to that. And then we put the reinforcement not beyond that. So then it will yield after that moment. So this is the section of this beam. So this has a width of B and H, and it says the shear capacity. So if you calculate the beam, this one, you can calculate the shear capacity, right? So let's say the shear capacity is equal to 100 kilonewton is the maximum shear it can take based on the size and the maximum reinforcement that you can put, right? Capacity from the code. So now you know that. And this is the length. So this is the length, let's say, is L. So just now, as I told you, the moment here is the one that is going to produce this shear. And this shear is going to be the moment divided by L. Total moment divided by L. So which means that you can correlate this shear back to the moment. And from there, you can say, okay, my moment So this will be the capacity. So the capacity moment diagram will be here. We'd say my moment is fixed at 120 based on whatever that shear is. And then any moment above that, if it comes like this, it will not exist because the reinforcement that you put is based on 120. So it will yield and come back to 120. And then the shear will not break. So which means below 120, it will behave like an elastic beam. It will try to hold the walls together. After 120, it will just let them go, holding 120 always and not breaking. So which means we limit we put like a certain fuse in the wall that it will make sure that the buildings, the two shear walls are coupled to a certain level. And beyond that, that coupling will remain, but deformation will increase, but it will not break. And sometimes that extra moment will cause it to crack, yielding will occur, but people can come and replace it. But it will not let the building fall, because if it breaks, everything goes, because the walls will become uncoupled, and that we don't want that. So that's the basic principle of link beams and coupling walls, that we design them to resist a certain amount of shear, and we put the reinforcement corresponding to that shear, and then we limit there. So this is the principle of seismic design, that we prevent the shear failure by limiting the moment capacity. Because in this case, unlike gravity load, we cannot do it for gravity load, because for gravity load, the shear is being produced first. So there's nothing we can do. But in here, the moment is being produced first. That's why I told you many times that lateral load moment comes first. So if you limit the moment, you limit the shear. So that's the whole idea. We can do the same thing for columns. So we can make the whole structure limited by shear capacity, never ever to have shear failure, but allow it to deform. So this is the principle of coupling for coupled shear wall and frame shear wall coupling. Same principle. We always design it for a specified shear capacity, limiting the moment, and hence limiting the capacity for interaction. So now look at this one, coming back to the comparison. So this is two walls connected by a very small beam, link beam, just a flat slab, nothing. This is a little bit bigger beam. This is a bigger beam. This is a even bigger beam, right? So as you increase the size of the beam, what do we find? Let's see. So deformation. So look at the deformation. Look at the deformation reduced a lot. And here deformation very small, right? Compared to that one. So that means as you increase the size of the link beam or the coupling, you control the drift, you control the displacement, you control everything. So that is one thing. The problem is that the forces in this one will become very large. Then you will run into this trouble that will fail in shear. And then you have to make sure that it doesn't do that. So you go back and go to something like this. Okay. So that's why the size of the link is normally fixed by architecture. You cannot change it because of the head clearance and all, and the floor height. So you cannot change it. You cannot increase the size by yourself if the shear increases. So if the size is fixed, that means shear capacity is fixed. If the shear capacity is fixed, you fix the moment by putting the reinforcement, which is not beyond that. So this is the bending moment happening in each one of them. Here, bending moment is increasing as you increase the size. And that is the axial forces happening. The wall axial forces are changing. The whole response of the wall is changing. Here, the two walls are bending independently. So you can see tension, compression, two colors here. So each wall is acting as two separate walls, right? Independent. Here, the tension compression is now shifting a little bit. Here, it is completely shifted from here to here. There is no more local bending of each leg. The whole wall is bending together as one big element. And that's what we want. Increase the stiffness from that individual. So this is 1 + 1. This is 1 + 1 multiplied by some factor. Okay. So you got tremendous increase in stiffness and benefit. So that is the shear. So very small shear, very large shear, very large shear. And this shear may be more than the capacity. So that's where you limit the capacity based on actual, and then you will limit the moment based on that. Okay. So everything is controlled by the shear capacity of the link beam. So please remember, all link beams are designed based on their shear capacity. And your idea to put the diagonal is one way to increase the shear capacity and make it more ductile. And sometimes we put steel bracing there. Sometimes we put the steel beam there because steel is very good in shear. So the coupling beams, if you cannot manage the forces, you put a steel there. Sometimes you put a damper there, a flexible capacity damper, which has the capacity to deform without breaking. So it's a lot of ways that you can use these link beams. And you can see here forces generated in the foundations here, completely changing. Please note this carefully if you can see. Here, compression, tension within one each pier. This column, this corner is compression, this is tension. Here, this tension gradually reducing. Here, the entire leg is in compression, entire leg is in tension. That means they are completely connected now as one part of the single structure. They have been connected to behave as one. Instead of two separate walls, they're completely coupled. So here they're fully coupled. Here they are not coupled. Here they are almost coupled, right? So you can see the coupling effect from the change in the axial forces and change in the foundation load. So there's this whole picture is quite rich. These 4 slides, starting from here to here, to here, here, all these are very, very informative if you understand them well, because it completely shows how the coupling effect is changing everything. Stresses, shears, moments, axial forces, foundation reactions, affecting everything. And that is your trick to use 1 + 1 more than whatever. So it's up to you to get as much benefit as you can. So flat slab perimeter systems, as I told you, sometimes we can have a coupled wall here and then put the flat slab in between. So it's no problem because these two extreme walls are taking all the load.